All right, so this video is going to focus on intermolecular forces, and we'll see how long it gets. We may get into a little bit of states, or we may split it up. So intermolecular forces are forces that are found between atoms or ions or molecules, not within. That's what we see with bonds. And these forces are what cause substances to exist in various states, whether they be solids, liquids, or gases. The states are determined by the strength of these forces as well as the types of those forces. Solids and liquids are typically described as condensed states because these forces hold the particles near to one another. They stay in close contact while in those states. They impact on the values or the temperatures that we see for melting and boiling points, as well as whether substances are able to dissolve in one another. We'll spend more time on that with solutions. State changes are known as physical changes because they do not result in bonds being broken and new bonds being formed, but they do result in these attractions that exist between molecules being broken, these intermolecular forces, rather than the intramolecular forces, which we know as bonds. So the first type of intermolecular force we're going to speak about are London dispersion forces. These are forces that can be found in pretty much any molecule or ion or atom, but they are going to dominate the type of intermolecular force that we find in our nonpolar molecules or in our neutral atoms. These result from instantaneous dipoles forming in these atoms or molecules. What do I mean by an instantaneous dipole? These molecules and these atoms all have electrons. And what will happen is as these electrons are moving around, more of the electrons will end up on one side of that atom or molecule than the other side. And so that's when you have a partial negative charge and a partial positive charge. And because these just occur from random movements, they are instantaneous. The ability of an atom or a molecule to form these instantaneous dipoles is known as polarizability. And we tend to see this with our atoms that have more electrons, whether they be in molecules or individually as atoms, because they just have more of these particles moving around that can become unevenly balanced throughout that atom or molecule. So again, this is the dominant type of intermolecular force that we see with our nonpolar molecules, as well as our noble gas atoms. Also some of our non-metal atoms, I would say, fall into this category. The metal atoms are going to do things a little bit differently, but this is pretty consistent with your atoms on the right-hand side of the periodic table, as well as your nonpolar molecules. Dipole-dipole forces are going to dominate in just our regular polar molecules that have permanent dipoles, partial negative and partial positive charge, due to those lone electron pairs, the multiple bonds, or just different electronegativity values being shared between bonds because you have different atoms present. They line up electrostatically so that the charges that attract to one another are going to be drawn closer together, and they try to minimize those repulsions, try to get the positive charges away from other positive charges and the negative charges away from other negative charges. We tend to see more of these dipole-dipole forces found in our liquids, and as the distance between these molecules becomes larger, these attractions aren't going to be as strong. So as the molecules start moving around more and they're getting closer to their boiling point, the dipole-dipole forces are not going to play as significant of a role. And so one example there is H2S. The sulfur would have 2 lone electron pairs, which is what would cause there to be a permanent negative and a permanent positive charge in that molecule. Hydrogen bonds are a specific type of dipole-dipole force. And so this is not going to apply to every polar molecule, but only those that contain the electronegative atoms N, O, or F. And to have hydrogen bonding occur, hydrogen has to be bonded to one of those electronegative atoms. So molecules that have hydrogen bonding are going to have the strongest type of intermolecular force that we see among our molecular substances. And so examples there include NH3, H2O, and HF. The last one we're going to talk about are the ones that we find in our ionic compounds, and this will not be found in anything molecular. These are known as electrostatic or ionic forces, and they are interactions that occur between oppositely charged ions, and they play a key role in the large values we see for meltings and boiling points of these ionic compounds as well as metals. So these are going to play a role with metals. We'll talk about that a little bit more when we get into metallic bonding. But ionic compounds and your metals are the ones that are going to have these electrostatic forces present. So some factors that affect the strength of your intermolecular forces. The first one are the type of compound. As we just talked about, your ionic compounds have stronger intermolecular forces because of those electrostatic forces, the permanent ions that form from the electrons being transferred, as opposed to your molecular compounds, which could have London dispersion, dipole-dipole, or hydrogen bonding. The length of the compound will also play a role. If you have a longer chain making up part of your compound, you have more places where those intermolecular forces can form due to the greater surface area. And if you have more of those intermolecular forces, that can have a greater impact than maybe one single place where dipole-dipole forces could occur. And then finally, the size. We talked about the polarizability. The larger your molecule, the stronger your IMFs, just because you can have more of those IMFs present. So here we have NH4Cl, and I want to know what are the most important types of intermolecular forces present in these solids. So NH4Cl is an ionic compound, so it's absolutely going to have electrostatic forces. It also could have some dipole-dipole forces because it definitely has a polarity to the molecule. If you had just put electrostatic, though, I would have been totally fine with that. But again, it's electrostatic because it's made of a cation and anion. It's an ionic compound. Here we have polyethylene, which is just a bunch of carbons and hydrogens bonded to one another. Carbon and hydrogen have very similar electronegativities, and because it's consistently bonded in the same manner, this would be a nonpolar molecular substance. So that's going to limit the possibilities for your intermolecular forces. This one can only have your London dispersion forces. Here we have chloroform, CHCl3. So this is a polar molecule because the carbon is not just bonded to hydrogen, but also to each of the three chlorines. Carbon is the least nonpolar of these choices here that can go in the center. Hydrogen cannot, but the bond between carbon and hydrogen is going to share electrons differently than the bonds between carbon and each of the chlorines. So because this is a polar molecule, it has to have at a minimum dipole-dipole. It can't have hydrogen bonding because it doesn't have the electronegative atoms. So dipole-dipole would be our choice. And now we have NH3. Ammonia is a polar molecule and it is capable of hydrogen bonding. So that's going to be the dominant type of intermolecular force present. It could have some dipole-dipoles because of its polar nature, but hydrogen bonding is the one typically that would be the most important type of intermolecular forces. I said the most important types. If you had just said hydrogen bonding for NH3, I would have been totally fine with that. Dipole-dipole would not have been sufficient, though. You did need to include the hydrogen bonding because it is a stronger intermolecular force than dipole-dipole.